Okay, this final segment of the lecture two, let's first answer the exercise questions. Uh, the first question asks you to show that the same procedure led to Lorentz transform can lead to Galilei if we impose the absolute time. And so that's the relative uh, coordinates when they move with v. And so therefore t prime is equal to b1 x plus c t. So if we impose x prime equal t absolute time, of course means there cannot be any position dependence, so b1 has to be 0 and a1 has to be 1. And then this transformation immediately reduced to Galilei transformation. Okay. And we're asked to write down the Lorentz transformation for coordinate derivatives, how they related. Again, since from the hint we know that this must undo the coordinate transformation. Here is the coordinate transformation. To undo this means the derivative must transform as an inverse transformation, which simply change the sign of the v. So therefore, the inverse transformation must equal to, just like this one, gamma, instead of just change sign. So that's the transformation for the derivatives. So now we have written down the Lorentz transformation. Now we're going to see the physical implications of such a transformation. In particular, we're talking what's called time dilation and length contraction. It means a moving clock appears to run slow and a moving object appears to contract. Okay. Now, we use the word here appears. You should understand that does not mean these effects are illusionary. Okay. Because a moving observer will find such a result in the measurements performed in his or her reference frame. Compare the measurement by an observer in the clock's or object's own frame of rest. So, uh, it's really different observer will make different uh, physical measurements. They are physical results. They are not just illusionary effects. Let's first talk about time dilation. Here's the Lorentz transformation written in term intervals. Now, when we say compare time to the rest frame with the moving frame, so if O prime is the rest frame of the clock, if it's a rest frame, meaning the clock's not moving, so there's no displacement, so the x prime has to be equal to 0. If you set the x prime equal to 0, then the dt must equal to vt. If you plug into the second relation, you find that both have dt. I can factor out. So dt prime, the gamma 1 minus v squared over c squared dt. But this coefficient simply is 1 over gamma squared because gamma is equal to square root. Okay, so therefore the relation is dt because when the gamma cancels, is gamma multiplied with gamma dt. And the gamma is greater than 1, so therefore the interval dt for the moving clock is greater than the interval in the rest clock interval. So the moving clock will run slower. Now, these are just from formulas, as so we really need to study a physical example to see what I mean, where this time dilation come from. So we can work out a concrete example. Now, for the concrete example, I can use a light clock to record the time. Okay, we could have used any clock. We could use a pendulum. We can use, in fact, any physical effect can be used as a clock. But we choose a light clock because I'm going to measure the interval by having a light pulse bouncing up and down between two reflectors. And the reason is because clock have this property directly connected to the basic postulates of special relativity. it was the propagates with the same velocity, same speed in any frame of reference. Okay, and so if you use, for example, if you use the pendulum, that's fine too. But you have to realize the equation to describe the pendulum no longer given by Newtonian physics. It has to be because that equation has to be relativistic. And so the relation between the interval and time is no longer as simple as in the Newtonian case. So therefore, the pendulum will not be a convenient clock to use. Even though if you use it after many steps, you will still get the same results. Okay, so for uh, in fact, you will see that's why the light signals is so important to use for talking special relativity, because it direct connects to the basic postulates. So if in one frame, in the rest frame, this clock, let's say, let's O prime, and then the distance traveled divided by c give you the dt prime. That's the time takes bouncing from one side to the other. Now, for a moving clock frame in which the observer is moving to the left and sees the clock moving to the right, then the light has traveled diagonal piece, big D, which is a longer distance than D, so take a longer time. Okay, so dt now is big D divided by c, and the big D is a longer distance, but the Pythagorean theorem is small d squared plus v squared dt squared, because this here vt squared square root. If I square on both sides, I have c squared dt squared in what's inside the square root, and then dt squared, because both have dt are combined together, equals c squared minus v squared, divide them, so d, and then divide by both sides, numerator denominator by c squared, I get this. But d over c is d prime squared, so therefore dt equals dt is related to dt prime, or in terms when we take the square root, that's simply the gamma factor. That's exactly the relation we have the time dilation derived from Lorentz transformations. But this, you can see, is really related to the fact the speed of light is unchanged in a moving frame. But in a moving frame, you have to travel a longer distance, so therefore the time interval has to be longer. Now we'll tackle length contraction. Again, first let's look how it came from the Lorentz formula, and then with concrete example to see how the length contraction comes in. Here's Lorentz transformation formula. Now, to measure a moving object, its length, we must involve two events. One is to measure the location of the front end, and another measure the rear end. So we must specify the time interval of the two events. Okay. So for example, you want to measure the length of a moving car. It's zipping by. So you want to measure the length. So you have to measure the front end, the rear end. So whatever it is, you have to specify when you measure front end, when you measure the rear end. In terms of formula, of course, the simplest, we choose the interval to be 0. I find a way to measure the front end and rear end simultaneously. Okay. On the other hand, if we talk about measure the length in the rest frame, the dt prime, so dt prime doesn't matter if you measure the length of a parked car. It doesn't matter when you measure the front end or the rear end. You can measure the front end, take a lunch break, and come back to measure the rear end. It's still there. Okay. So key thing is the time interval in the moving frame. In this case, we simply we choose to be 0. Okay. If you not choose 0, it's a little more complicated, but it's still the same. So if we set dt equals 0, then relation between dx prime simply dx prime minus gamma. Now gamma is bigger than 1, so therefore the dx is smaller than dx prime, so therefore length contraction. So moving object is measured to be shorter. Now this result is counterintuitive. It came from kinematics, and you will see it's again related to time, because the Einstein new conception of time will lead to such a counterintuitive result of length contraction. So we're going to work out a concrete example in the next slides, show how the time dilation actually enters into the conclusion of length contraction. So now we're going to measure the length of a moving rail car. Okay. So what we're going to do is that we're going to have a clock fixed on the ground. And for the observer on the rail platform, the rail car is rushing by. Now, when the front end just crosses this point, when the clock located, we record time t1. Okay, and of course, then we record the time when the rear end of the train passes through the clock. We call t2. Okay, then the observer can deduce the length of this moving rail car by taking time difference, multiply the speed of the train, and so that's the length of the train. As far as he's concerned, that's how you measure the length of the moving rail car. Okay. Now, for observers who is sitting on the rail car itself, you can use the same clock on the ground to deduce length. Okay, you can observe the time when the front end passes the clock on the ground. We call that t1 prime. And the same way, when the when now you see to him, it's the clock is rushing by to the left. Okay, so when the clock just passed the rear end of the rail car, he again look at time. That's t2 prime. Then t1, t2 prime difference multiplied by v, then it gives you the length. So that's how he deduced length of the rail car. Okay, so in the rest frame of the rail car, he can deduce this way. So let's remind again. The x prime is length, the rest frame length, and the x length of the moving railroad car. And they're given by this related time this way. Now, so for the moving length, you have v dt. But that delta t, the time interval, is related to delta t prime by time dilation. Now remember, time dilation is that the moving time interval is bigger than the interval at the rest. Now in this case, delta t is the clock on the ground, on the platform, so therefore that's the rest frame. And here delta t prime is the rest frame of the rail car, but the clock is moving. So it's the moving clock measure. So that's so you be very careful, because remember last time we wrote delta t with that gamma delta t prime. So what you put t prime, that's don't confuse, don't blindly follow prime. You have to be very clear which is the moving clock, which is the rest frame clock time. Okay. So if this case, then this relation now I can replace delta t by delta transferred by gamma. So therefore, v delta t prime is delta t x prime. So here is time length contraction result. Right, talked all these things. Okay. So we have the length contract result. Okay. So you see now time duration and length all change under coordinate transformations for a moving observer. So now you wonder, is there anything that's not changed? I mean, if everything changes at the same time, are there anything that's unchanged, or sometimes we say absolute? Well, of course, we have the Lorentz transformation. It turns out that certain particular combinations are okay, because of course C prime is absolute, but also there's a particular combination of space-time interval and still absolute. It's unchanged. That combination is called S. So the S prime squared equals dx squared plus dy dt is just the length, but now minus c squared dt squared. And this combination is unchanged. So in the prime frame, they also have the same value. What would you do? It was just checking. So it was we want to check the S prime with all the prime. When I substitute the Lorentz transformation, it gave me the S squared back. So of course the transverse direction, nothing changed. So dy is dz squared. So the x prime squared becomes gamma squared dx d minus v dt squared. And for the dt prime, I have this. I have gamma squared. I have the c squared. I'm going to put it inside. Becomes c dt v minus t 1 to the power x t 1 to the power c cancel dx holding square. If I work out the square of this, to this equal to the x squared dt squared was a mixed term, and this is dt squared dx squared was mixed term. And I notice these two terms, they of course both have the same coefficient gamma, and I already put the minus sign here. So these terms, when I add them together, cancel. And the first, if I collect the dx squared term, so I have 1 minus v squared over c squared dx squared, and I collect the t squared term, c squared, again have the same 1 minus v squared t squared. So I factor out 1 minus v squared over c squared. I have dx squared minus c squared dt squared. That's exactly the combination we had for here. Okay. So therefore, the gamma square just cancel the 1 over gamma square here, and I have dx s prime equal dx. So this is combination of space-time interval are absolute. So you wonder, why should something like this should be absolute? Okay, what's this S? Turns out this S is directly related to something called proper time. Proper time is a name for the time measured in the rest frame of the clock. Okay. So in the rest frame, of course, there's no displacements. Dx, dy, dz all equals 0. So therefore, this S just displacement is gone. So therefore, just the time. So therefore, the ds squared is simply directly related to the proper time in the rest frame. Now, why should it be invariant? Because it's only one rest frame. So everybody, no matter where you are, what you're moving, you know which is rest frame, and you know what's the rest frame time. So therefore, the proper time should be all observers will agree on, and so that should be the invariant. Should be absolute. Okay, let's end the second lecture. So let's see the key point we have studied. And in fact, the transmission is not speed is not infinite. You have the relativity simultaneity. Okay, two events observed at the same time. In one case, it will be seen to be not simultaneous, another reference frame. So this led to a new conception time in which time measurements are coordinate dependent. So t prime in general does not equal to t. And so therefore, relativity and the constancy of c can be compatible. Relativity means the same physics in different inertia frames, and the constancy can be compatible. So we make these are the basic postulates. And first of all, we've shown immediately that equal to mc squared follows, and then we also shown the Lorentz transformation follows from the two postulates, and then the consequence of time dilation and length contraction. And then we then show a particular combination space-time interval which related to proper time is still absolute. In the third lecture, we will talk about the Lorentz transformation of electromagnetic field. Electric field, magnetic field, we view it to be at different values by different observers. And then we start chapter 3, which is geometric formulation of special relativity. And we will show something called space and time, which is four-dimensional space with time dimension as the fourth dimension. And then we show the Lorentz transformation that can be viewed as a rotation in space-time. So like xt can rotate to x prime t prime. So therefore, all we know about rotation and how the rotation symmetry can be used to discuss the Lorentz symmetry. And remember, in rotation symmetry, if you write in tensors, you're automatically symmetric. And the same way, if you write in term tensors, that's in the space and time, then the equations are automatically uh, symmetric, which is relativistic.